Hi, welcome to Mathematics with Tom. I'm Tom, and today we're going to learn about elimination, and we're going to encode it with matrices. So that's our title today, Elimination with Matrices. (2.3) Elimination with matrices. Okay, so let me do a little bit of review. We started out and we looked at this. We said we had some problem and it said solve. And it was a matrix equation. It was the matrix A multiplied by some unknown vector x equals the vector b. Okay? And then what we did is, when we first studied this, we then wrote this out as a system of equations and used the process of elimination, we used the process of elimination working on the rows, and then we would get down to this final state where we had the answer. And so what we would do is we would come down here, and so using row operations, and we would end with this result. We had an upper triangular matrix. We called that U. We still had the same unknown vector x. And not only had A changed to U, B changed to C. Not the scalar, but a vector. So with this in mind, what we're going to do is we're going to solve a system today. And then we're going to learn about how to put this into matrices. And then, well, let's just see how far that takes us. So here's what we're going to do. Today we're going to solve, and the matrix is this. It's, I might need to check my notes just so that I have the right problem for us. I have this written down. Solve, it is, right there. No, right there. Okay. The problem is 1, 2, minus 1, 4, 9, minus 3, minus 2, minus 3, 7. That's the matrix of A. Times some unknown vector x is going to give us the vector b. In this problem, it's going to be 1, 8, 10. Okay. Now, before we launch into our solution, what I would like to do is notice this, that when we were working on solving this problem as systems of equations, the x, the y, and the z, the variables, never changed. So rewriting this x through this whole process was just, well, it was just cumbersome because there was no changes. And so let's think about this. We're here at ax equals b. We're going to make a number of changes using row operations to end at ux equals c, and x again will not change. So I'm going to rewrite this and only take the pieces of it that I need. And so what we're going to do is we're going to take ax equals b, and we're going to write ax equals b as the augmented matrix. I'll use it. The augmented, there's your vocabulary for the day. The augmented matrix A we put a line after it. The line denotes the equal sign and the lack of the x's. B. All right, so let's work on that. So here's our matrix. There's the matrix equation. Let's write the augmented matrix. So we have a 1, a 2, a -1, and a 1. We have a 4, a 9, a -3, and an 8. And then we have a -2, a -3, 7, 10. Okay, let's just double check I copied everything correctly. Okay, now we're going to perform row operations, but we're going to be very systematic about it. But we're going to follow the exact same process that we did in the previous video. So what we're going to do is remember this top number here. This is our pivot. And our goal is to get zeros below the pivot. Zeros below pivot. That's our goal. Okay. Now, here's what we're going to do. We're going to do this very systematically. The first thing we're going to do is we're going to work on this 4. So I'm going to encode this. I'm going to write it this way. I'm going to create a new row 2. And I'm going to do that by subtracting 4 row 1s. Okay, I'm going to write it just like that. So if we're working on row 3, we'd start with row 3, and then we'd use our pivot row to make the changes. Okay, so we're always going to start with the row we're working on, and then reference our pivot row. So this is row of concern. Pivot row. Okay, I think we're ready. So here we go. Wow, I think we can put our next step. Now, we don't put an equal sign. Let's just use an arrow. Usually you just use an arrow because it's not necessarily equal. There's changes that have been made. For example, this matrix here is not equal to that matrix there, or U is not equal to A. So we're just going to use an arrow to indicate our progression of changes. So our first row stays unchanged. So I have 1, 2, -1, 1. Now, my second row, row 2, says you take 4, and then you take -4 times 1, so that's 0. Then you take 9 -4 times 2 for 1. Then you take a -3 -1 times -4 for 1. And then you take, this is the key, you always need to get this last column as well. You take 8 and you subtract 4 for 4. And then row 3 remains unchanged. So -2, -3, 7, 10. Put my line, and there's my new augmented matrix. Okay, and now let's make another change. Well, here's our pivot, still in the same place. This is still my pivot. So I have a 0 in the second row, so I need to get a 0 in this third row. So I need to work on row 3, row of concern. And in order to do that, I think if I had a -2 here and I added 2, well, that would give me a 0. So let's go plus 2 times row 1. Plus 2 times row 1. Okay, I'm going to put my arrow. This one might be a longer arrow. It's going to come all the way over here. And then let's make our changes. Now, the first 2 rows haven't changed, so let's copy those down. So I have 1, 2, -1, 1, 0, 1, 1, 4. And now we can make our next step. So this is minus 2 plus 2 times row 1, so that's a 0. This is minus 3 plus 4 for 1. This is 7 minus 2 for 5. And this is going to be 10 plus 2 more for 12. Put a line there. Really hope I got all my numbers correct. If I didn't, well, that's okay. We'll go fix them then. Okay. Now, our first mission, our first goal was to get zeros beneath a pivot, and we did. Well, what happens? Now, our next pivot, we come down along the diagonal. So this one right there, remember this is the diagonal. So that's where our pivots we always are looking for pivots along our diagonal. Non-zero pivots are ideal. This is our pivot, so I need to get a 0 below that pivot. So what do I need to do? I need to work on row 3 again. And I think I'm going to do that. All I have to do is just subtract row 1. And you know what? Just for clarity, need to subtract 1 times row 1. Now, obviously, not writing a 1 is implied. Row 2 would be a better work, yes. Thank you for my cameraman. So we're going to work on row 3. We're going to subtract row 2, and here's my arrow. Let's see where we end. So my first and second rows are unchanged. 1, 2, minus 1, 1. 0, 1, 1, 4. 0, now we have 1 minus 1 for 0. 5 minus 1 for 4. 12 minus 4 for 8. Oh, look at this. Here's our diagonal, 1, 1, 4. We have zeros below the in all the positions below the diagonal. We're done. This is the augmented matrix now of U, C. That's the augmented matrix for UC. The UC that we were talking about all the way over here. Okay, now we could write the solution if that was what we wanted to do. We would say that 4 times 8, well, let's do this. We actually, I think we'll write our solution in a moment. The solution's not hard. So what I'd like to do now is we need to come back and do some more prep work. So let's come over here. We're going to do some prep work, and here's what it is. We're going to work for today. For today, we're going to be working with square 3x3 matrices. And so let me do that. So I need to lay a little bit more groundwork here. Let's see, a matrix. Let's do this, matrix notation. Let's see. We'll call it B. No, we'll call it A. Let A be an M by N matrix. Okay, so what would that mean? This first letter here, M, is the number of rows. Oops, whoops. The number of rows. That's the M, and the N is the number of columns. rows, columns. Let's write it this way, A. So if A has m rows, here's how there's m rows. I'm going to write it, like, leave myself some space. Maybe I need to, this is m rows. An entry in the matrix of A, we'd use a lowercase a, very similar to like if when we used the vector x, we had script and we used the lowercase x1, x2, and x3. Well, what we have here is this first position, we always go row, column. So this first position is in row 1, column 1. So our second row would have A, row 2, we're in the same column, 2, 1. And we would continue this pattern all the way down, staying in column 1 until we get to our last entry, A. It's in the row M, column 1. And then let's come across. If we come across, we have the next entry would be A. This time it's still in row 1, but now you're in column 2. Then this pattern continues all the way across until you get A, and now you're still in row 1, but now you're in the nth column. So there's n columns. I'm going to abbreviate columns. M rows. And now let's see if I came down here, this is A, row 2, column 2. And it's kind of interesting, all of the entries along the diagonal are always the same row and same column number. Like this may be row I. Yeah, I'm not going to do that. Hang on. Let's, if we come down along the diagonal, we would have our last entry here is A, mth row, and the nth column. Okay? And then...
This is only square matrices.
No, this is any matrix now. M by n. This is true.
Okay.
Oh, yeah, about the diagonal thing?
Yeah.
Yeah, I shouldn't have said any of that. I'm going to have to go delete that.
Yeah.
Yeah.
That doesn't work unless it's square.
Right, yeah, because if it was...
The diagonal wouldn't get to the corner.
Yeah, it'd be like down here somewhere. Yeah, I shouldn't have said anything. Yeah, you're right.
Okay, you just wanted to...
Yeah, no, you're on your game. I think. Okay, so there's my matrix. Oh, and in general, if you want to just pick just some random value in some row and some column right here, you'd say it's Aij, where it's in the I row and the J column. So that's how you talk about just any entry in the matrix of A. It would be Aij. Okay? Now, we need a little bit more. So our problem today was a 3 by 3 matrix, 3 rows, 3 columns. And what we're going to do now is I want to introduce something that we have kind of tripped upon, and that is the identity matrix. We're going to start with an identity matrix. So if the identity matrix is, in our case, we're going to use one that's 3 by 3. So let's do it this way. We're going to do let I be, there we go, 3 by 3, because I can be 4 by 4 or 2 by 2. So what that means is the identity matrix, that's what this stands for, identity matrix. And it's the equivalent of the multiplicative identity 1, but in the world of matrices. So this one looks like this. It's a 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the 3 by 3 identity matrix. Okay? What happens here? It's always this pattern. If it was a 4 by 4, then your fourth row would be 0, 0, 0, 1, 0, 0, 0. It's always this pattern, 1's on the diagonal, 0's everywhere else, and it's always a square matrix. Okay. Let's see what happens. So for example, if I want to take, I have a B. I have a B over there. It's a 1, 8, 10. If I take I and I multiply it by B, this is 1, 0, 0, 0, 1, 0, 0, 0, 1. And let's multiply this by B. I just want to show you that it works. We had 1, 8, 10. That's my B value, B vector. So watch what happens. Now remember, when we multiply a matrix times a vector, and you're just trying to get the numbers, then it's easiest to use the dot product of the row with the vector. Then the next one will be row 2 with the vector, and then your final entry will be row 3 with the vector. So notice what happens. This is row 1 says you're going to pick up 1 of the first elements plus 0 of the second elements plus 0 of the third element. So you get 1. The second one, watch what happens here. So notice the first row dictate what goes into the first entry of our vector. The second row will dictate what goes into the second entry of our vector. The third row will dictate what goes into the third entry. So watch. Well, now what does this say? This says you're going to take none of the first one, 1 of the second, and 0 of the third. So 0, 1, 0. So this is going to be an 8. And finally, the third row says you want 0 1s plus 0 8s plus 1 10. Or 1 times 10. So it worked like we thought. I times B just gave us B, which is exactly what we anticipated. Okay, are you ready? This is where it gets interesting. Change, single, let's just call them that, single changes. Okay, I can write that better. Single changes to I form the matrix E. The matrix form the matrix E I J, where the changed value we'll call L, and L goes in the IJ position. Okay, I'll explain that very carefully. And we're going to try one. So now we can only make one change. And when we change this identity, we're not going to change the diagonal. We're just going to play with the zeros. We're going to just play with the zeros. So for example, you might denote this different ways. Let's say L, we could even change it. Let's say L equals, let's try -2. It's easy to track. So we'll do this. Let L equal that. Let L equal -2. Try E21 times B. E21 times B. So let's write that down. So E21 times B. Here's what it looks like. The E matrix is just like an identity, except for one position is changed. So I have 1, 0, 0. Now we're changing the row 2, column 1 position. That's this next line. Row 2, column 1 will be right there. And we're going to call it -2. -2, 1, 0, 0, 0, 1. And then what are we going to do? We're going to multiply that by B. 1, 8, 10. Okay, so watch what happens. Remember what we said. What we said was the first position, the first row of my new vector will be dictated by the first row of the matrix. Well, we've already done this. This is just one, this row times this vector gives us a 1. Now, here's where it gets interesting. This row 2 is now dictated by this. Well, what does it do? I'm going to write this out. It says you take -2 times the first times 1. You add 1 of the second row, which is an 8, plus 0 from the third row, which is the 10. And then this row 3 is going to just say is going to remain unchanged. Well, what did this do? This gave me the result of 1 minus 2 and 8 is 6, 10. So what this just did, what did this do? E21 took row 2 of B, and what did it do? It added to it plus -2 times row 1 of B. Now you might be like, really? Yes. And we're going to try a few more though, because I don't think this is immediately obvious. So what can we do? Oh, let's try this. Let's do, we're going to use the same L, and let's try E31 times B. And let's see what we get. And then we'll try one more at pace, and then we're going to go a little faster here. So E31 means you change row 3, column 1. So there's row 1. Row 2 is the same as you expect. And then this says in row 3, column 1, we're going to put that L of -2. And we're going to multiply that by B. B is 1, 8, 10. Okay. Well, this says in the first position, my first row, it remains unchanged. It's just 1 of the first one plus 0 of row 2, 0 of row 3. Again, the second row remains unchanged. It says you take 0 of the first row, 1 of the second row, and 0 of the third. Now watch what happens here. This says you take -2 of row 1, nothing from row 2, and you take 1 from row 3. So this becomes a -2 plus, or else do this, -2 times the 1 plus 1 times the 10. That's the row 3 position. So this is just going to give me the vector of 1, 8, 8. Okay. Now, in other words, what did this do? This is really taking row 3 and it's adding to, or it's taking a -2 times row 1 and it's putting it into the third position. Let's try one more. What about if I had, let's switch them. Row E1, we'll try that. First, let's do that one. E3, 2. E3, 2. What would that do? Well, that would mean that the negative 2 is in this position. So what that would do is, since it's in the third row, it's going to affect the third row, and it would take whatever L is, negative 2, so this would be this. This is the row operation. The row operation of row 3 minus 2 times. Oh, I made a mistake, didn't I? It's not 2 times row 1. It's in this second position, so it's 2 times row 2. There. Let's try another one. Let's switch these. What if I had 2, 3, row 2, third position? Well, this is kind of an odd one, but what this would do is this would give me the row operation of row 2, and then we would be subtracting 2 times whatever is in row 3. So, I mean, we probably wouldn't do that very often, but we could. All we have to do is move L into different positions of E and effectively create row operations. I think we're ready to put this together. And to do that, I'm going to have to come back over here. But you know what? We have all the work laid out before us. So I'm going to come over here with my eraser. And let's come back. We have 1, 2, I'm sorry. 1, 2, 3 row operations right there. So let's write that. Okay, what was this? Well, this right here, I'm going to call this step 1. In step 1, our matrix, our E matrix is E. We worked on row 2. So this is me at E2. And we changed row 2 by referencing row 1. And what did we do? We multiplied it by a negative 4. So this is the E matrix of 1, 0, 0, minus 4, 1, 0, 0, 0, 1. Our second one, number 2. Our second one is right here. Our second one, well, this time, our matrix, we were working on row 3, and we were doing that by using our pivot in row 1. And the change that we use is we took 2 row 1s. So this is 1, 0, 0, 0, 1, 0. What do we have? 2. 2, 0, 1. And then our third operation, our third one, is right here. Notice what did we do? We worked on row 3 by referencing row 2. So this is an E, 3, 2. And what did we do? Well, 1, 0, 0. We have 0, 1, 0. And in the 3, 2 position, we have a 0, minus 1, 1. Okay, now it's time to put this all together. All of this together. So I'm going to take some board space back. Good thing we had left all of that. And okay. Now, here comes the big step. Here comes the big step. We started with this. We wanted to solve the problem AX equals B. And now, this is not a general A like I erased here. This is that A over there, our starting A. And we made all these row operations to get to UX equals C. Well, wait a minute. Now we've just written these row operations as matrices. So what did we do? Well, we took E 2, 1, and if we multiply that on AX equals, on the left side, E 2, 1, and then also on the right side, we are going to make that first set of row changes. But then what did we do? Well, then we took this and we multiplied it again. We made another row operation. That was E3, 1. And we did that to the result of E2, 1, AX. And we did that over on the other side too. E3, 1 times whatever this was. E2, 1 times B. But then we did one more row operation. This row operation can be encoded as this matrix. So now we took E3, 2, and we multiplied it by this result. E3, 1, E2, 1, A. X, and then E3, 2 on whatever this was. E3, 1, E2, 1, B. And what does all of this give us? U. X equals C. Now, you may right now be a little uncomfortable, and that's good. And here's why I'm hoping you're uncomfortable. Because so far, all we have done in this class is taken a matrix times a vector. Well, wait a minute, but what is this? This is a matrix times another matrix. We haven't done that yet. Well, I want to show you how that works. So, I think you'll see, you may even know before I tell you, you'll see it happening. Let's try this first piece of multiplication. E2, 1, E2, 1A. So let's just write these down. This is 1, 0, 0, minus 4, 1, 0, 0, 0, 1, times the matrix of A, which was 1, 2, minus 1. And you know what? We're even going to, yeah, we'll just do that. And then we're going to have a minus, 4. 4, 9, is it minus 3? It's been, I got to look back. Minus 3. And then a minus 2, a minus 3, and a 7. And you know what? Just for interest's sake, let's put B in there. We'll just use the whole darn augmented matrix, the whole thing, all at once. Once you see it, you'll get it. Watch what happens. What is the matrix of A? Well, this first column is a vector. What is the second column? It's just another vector. Well, what is this third column? It's just another vector. And what is that fourth column? It's another vector. In other words, multiplication of a matrix times a matrix, it can be thought of as the new result would be the E2, 1 times the first column vector of A. We'd call it, this is a boldface A. Notice it's not an AIJ, but it's this. And then the next entry will be E21 times A2. This. And the next entry in our new matrix is going to be E21 times A3, the third column in the A matrix. And the last one will be E21 times B. So you've never learned formally, and we'll do it soon, matrix multiplication, but you've already really know how to do it. So let's try. Let's try. This says we're going to take, and let's do this multiplication. Our first column says we just want one, we're just looking at this row and this vector. It just says we want one copy of the first of row 1. This next one says we're going to take minus 4 of the first one plus 4 of the second. That's a 0, or plus 0 of the third. And then this third entry here, it says we take 0 of the first, 0 of the second, and a minus 2. Now we're working on E21 times the second column. And we just repeat. This says you take the first entry, 2. This says you take minus 8 plus 9 plus 0. That's just 1. Then you do it again. This just says we want just the third entry, minus 3. And then we take the next one, E21, and we apply it to this third column. So we're going to pick up a minus 1. Then here we're going to have a 4, minus 3 plus 0. And then our last one's be 0, 0, 7. And our E21 times B says we're going to pick up one of the first ones. We're going to take minus 4 plus 8 for 4, and then a 0, 0, and then a 10. If I did that right, that is the second time I've written this on this board. Let's see. Here it goes. I'm going to come over here. Got my fingers crossed. You should too. These always make me nervous when they're on camera. And there it is. Look at that. That's the exact same result as doing those row operations. Okay. Now there's another question you probably are already thinking to yourself. Can I just put all those together? And the answer is yes, you can. You can. So what you can do now is you want a final E. So really we want some matrix E that when we multiply it by AX and we multiply E times B, our result is UX equals C. And E is right here. Oops, that's not E. E is the product of our elementary matrices. So let me write that. Okay, so E is the product of the elementary matrices. Elementary matrices. E, I, J. So for our problem here, E is the result of E32, E31, E21. Now, there's something very important here. Notice that when I wrote these, the order matters. I have to. The first thing I did was this row operation. So that's the first. That has to be the first one on the right because it multiplies right here with A. Okay. Then the next thing I did is I multiplied by E31. That was the second row operation. And then the next thing I did was E32. That was my third row operation. So the order of the e's matters. And we aren't going to show this yet, but when you multiply, notice I multiplied the e's on the left side here. I also multiplied the e on the left side of the b as well. It won't make sense otherwise. So if you multiply on the left here, on the left side, you multiply on the left on the right side. So the order matters. And then what I would encourage you to do, now what doesn't matter is these are associative. You could start here, E3, 2, E3, 1, E2, 1 if you wanted. Or if you wanted, you could multiply it as E3, 2, E3, 1, E2, 1. And I would encourage you to try all of those. So what I'd like you to do is take a moment. I'd like you to stop the video, and I would like you to find this product. Find this product, okay? Stop the video. While you're thinking and pausing, I'm going to go and I'm going to write down that result, and then we're going to show you how it works. Okay, 6. Okay, we're back. This should have been the result of E32, E31, E21. And so for our final step, what I'd like to do is let's take the matrix of E, let's multiply it by the augmented matrix AB, and see if in fact we get UC. That's our goal. So I'm going to just change this a little bit. There's E. Since I don't have a lot of room, we'll make this E times AB. So that's going to be 1, 2, minus 1, 1, 4, 9, minus 3, 8, and minus 2, minus 3, 7, 10. All right, and let's see, do I get UC? UC, so if we did all of this correctly, we would end up with this matrix right here. Okay, let's do that. Let's check. So this says we're going to have first position. Oh, this is going to be a big one. So we take this matrix and we multiply it by the first column. Then we take this matrix and the second, third, and fourth column. So here we go. So that's going to be a 1 in the first spot. And then if we're now going to do row 2 times the second times this first column, so that's going to be a minus 4 plus 4, that's 0 plus 0 more. Then we're going to take the third row on the first column, so that's 6. 6 minus 4 is 2. Is that right? Oh, I'm sorry. 1. That should be a 1. Minus 2 more, that's a 0. Hopefully you guys caught that. And then, let's see, then we're going to start we're going to work on the second column. So we have a 2. And then we have the second row. That's going to be a minus 8 plus 9 is 1 plus 0. Then we have a 12 minus 9 for 3 minus 3 more for 0. Then we do this again. So we have a minus 1. And then we have, that's going to be a 4 minus 3 is 1. Then we have minus 6 plus 3 is minus 3. Minus 3 plus 7 is 4. And then our last one is we have a 1. We have a minus 4 plus 8. Then we have 6 minus 8. That's minus 2 plus 10 is an 8. And there it is. And that is how you encode the steps of elimination into matrix multiplication. Thanks for watching.